Hi there, I'm Graham Lewis, and in this video we're going to consider the function y equals x to the power 5/3. Find the critical points and classify them and use that to help sketch the graph. So firstly, to find the critical points, we either set dy dx equal to 0 or we look for where the points are undefined for dy dx. So let's find dy dx first. So dy dx, using the differentiation rule, the 5/3 comes down, and we knock a power off 5/3 to give us 2/3. So we have 5/3 x to the 2/3. Now clearly, when does this equal to 0? This clearly equals 0 when x equals to 0. And 5/3 x to 2/3 is never undefined. So we've got one critical point when x equals 0. So now let's try and classify this. Of course, it could be one of three things. It could be a local maximum, it could be a local minimum, or it could be a horizontal point of inflection. So a local maximum, of course, has a slope of 0. Local minimum, of course, has a slope of 0. And there are two types of horizontal point of inflection. It could be concave down and then change it to concave up, or concave up and then change it to concave down. So one of those. 4. So let's find the second derivative and see if we can classify this. So we've got dy dx equals 5/3 x to the 2/3. So if we find the second derivative, d2y dx squared, so that would be 5/3, bring down the 2/3, knock power off, and so we get 10/9 x to the power minus 1/3. And maybe a nicer way of writing this would be 10/9, and clearly what x to the power minus 1/3 is 1 over x to the power 1/3, which is of course the cube root of x. So I've got 10 over 9x to the power 1/3. Now we're interested in our critical point, which is x equals 0, and we can see that at x equals 0 our second derivative is actually undefined. So that's not very useful. That doesn't tell us anything. Obviously, if the second derivative was positive, it would have told us the function is concave up, and we would have had a minimum. If the second derivative had been negative, it would have told us we were concave down, and we would have had a maximum. But the second derivative is undefined, so it's inconclusive. We need to explore a little bit further. So let's have a look at a slope chart. So in this slope chart, we're interested in our critical point at x equals 0, and just to the right of it and just to the left of it, what's happening to the slope and the function. So the slope function dy dx is 5/3 x to the 2/3. So the slope function is 5/3 x to the 2/3. And then I'm interested in what that tells us about our function y equals x to the power 5/3. So let's put minus 0.1 in, and actually I'm only interested whether it's positive or negative. When you put minus 0.1 in, you're going to square it, which will make it positive. Cube root, still positive. Times by 5/3, still positive. So clearly this is a positive number. When I put 0 in, we know that the slope is 0, that's our critical point. When I put 0.1 in, clearly 0.1 squared, cube root, times by 5/3, positive. So I know that the slope is positive, then the slope is 0, and then the slope is positive. So for the function. So you can see with that shape there that we clearly have a horizontal point of inflection at x equals 0. And it is, the point is actually 0, 0, isn't it? You sub 0 and you get 0 out for y. Now, to sketch this, it might be interesting just to think about whether it's an odd or an even function. So let's explore y equals x to the power 5/3. Now, if you remember, I'll write that in function notation, f of x. If we explore f of minus x, which would be minus x to the power 5/3, and let's see what that's equal to. So I can write that as minus x to the power 5, and then the cube root. So minus x all to the power 5 is minus x to the power 5, or cube root. And then the cube root of minus 1 is minus 1. So I can rewrite this as minus x to the 5/3. So what we've shown there is f of minus x equals minus f of x. So it is in fact an odd function. Now, of course, odd functions have symmetry of order 2 about the origin, so I know that it's got symmetry of order 2 by the origin. I also know that as x tends to infinity, y tends to infinity, and as x tends to negative infinity, y tends to negative infinity. And I know it's got a point of inflection, and I know there are no other maximum minimums or anything, so it's pretty easy to sketch this now. I know it comes up, has a point of inflection, and then goes back up. And that's what it looks like. And it might be useful to look at the actual graphs of these three functions, the original function, the first derivative dy dx, and the second derivative d2y dx squared, on the same set of axes. Notice a few things. When the original function is concave down, which is in here, the original function is concave down for x less than 0, notice that the y values of the first derivative are decreasing, which means that the y values of the second derivative are negative numbers. So when the y values are negative numbers of the second derivative, it means that the y values for the first derivative dy dx are decreasing, which of course means concave down. Notice on the right hand side of the original function here, it is actually concave up. We can see that the tangent lines are underneath the function. So when it's concave up, notice that if you look at the first derivative there, when it's concave up, you'll notice that the y values are increasing, and they're going up. The y values are increasing, and notice that the second derivative has positive y values. So when the second derivative has positive y values, we know that the slope function dy dx is increasing, and hence we know the original function is concave up. Notice at the point of inflection here of our original function, the concavity is changing from concave down to concave up, as we suspect, and also notice that the second derivative, which is the green function, changes sign. It's negative before, so you can see just before 0 the second derivative has negative values, and just after 0 it has positive values. So the second derivative changes sign, and obviously that indicates that it could be a possible point of inflection, which of course it is, because the second derivative has to change sign, which indicates a change in concavity in the original function. Thank you very much for watching this. If you enjoyed this video, please watch some of my others, and have a great day.